recording just in case anybody finds it useful. So this is the height of a Ferris wheel at time t, and we can see from the graph that t's in minutes. And if I'm thinking of what's really going on, if here's the ground, here's my Ferris wheel, the lowest we are is 10 feet off the ground, and the highest we are is 60 feet, which means from the bottom to the top is 50 feet. And that is the same as the diameter of the wheel. All right, so with the Ferris wheel problem, the amplitude is the same as the radius of the Ferris wheel. Okay. And how long does it take for the wheel to make a complete rotation? I think that's pretty easy to see from the graph. We're at the bottom here, and then we're back at the bottom 3 minutes later. So it takes 3 minutes. And we can assume the boarding platform loads us on at the bottom of the wheel. So the boarding platform is 10 feet. And it's important to put units. All right. And something that I think people don't always understand, I always find that when I teach this stuff, people get it down, and then when I throw in the horizontal shift, certain people think that you always have to have a horizontal shift. If you cross the y-axis at the lowest or the highest, you can use a straight up cosine equation with no shift. Or if you cross the y-axis on the midline, you can use a sine or a negative sine function with no shift. All right. I'm starting at the lowest point. I'm on the y-axis at the lowest point, so I want to use negative cosine. We can see the midline is y equals 35. We can see it, but we can also add up the 60 and the 10 and divide by 2. The amplitude is 25, and the period is 3. So our equation should look like this. Negative 25 cosine 2 pi over 3 t plus 35.
One question.
Yeah.
So the bottom unit is not 30, but 3.0.
Fair enough. Yeah. Yes, but I didn't see it until I really zoom in on it, and depending on what it looked like on your computer. So yeah, if you thought it was 30, then obviously you'd have pi over 15 as your number in front of t. But everything else should have looked the same.
Okay.
Okay. And yeah, that would affect your answers. That would be a pretty good value for your money, I guess, if it took you 30 minutes to go all the way around the Ferris wheel. You get at least a 30-minute ride, although it would be so slow you barely notice you're moving. All right, let's solve this one on the interval 0 to 6. When is the person's height exactly 20 feet? Why don't we go ahead and eyeball it? Here's 20 feet. So I'm going to just draw it out here. Here's the first time. Here's the second time. Here's the third time. And here's the fourth time. And these two are separated by exactly 3 minutes. And these two are separated by exactly 3 minutes, because I'm at 20 feet on the way up. Over here I'm at 20 feet on the way up. Here I'm at 20 feet on the way down. The next time I'm at 20 feet on the way down is exactly 1 cycle later. All right, so we're gonna most likely get this one from the calculator. We'll add 3 minutes to it and get the third one. We'll use the symmetry of the graph to get the second one. We'll add 3 minutes to it to get the fourth one. All right. So, but the distance from here to here should equal the distance from here to here. All right. So if this was 0.4, this distance would be 0.4, and my second time would be 2.6. And let me know if I'm talking too fast. All right. So let's go ahead and 20 equals negative 25 cosine 2 pi over 3t plus 35. Let's subtract 35 from both sides. Negative 15 equals negative 25 cosine 2 pi over 3t. I'm going to divide both sides by negative 25, and that's going to give me 15 25ths or 3/5. 0.6 is fine. All right, now I want to take the inverse cosine of both sides. So I'm going to get inverse cosine of 0.6 equals 2 pi over 3t. We want to divide by 2 pi over 3, which is the same as multiplying by 3 over 2 pi. And this is one that a lot of people get wrong on the calculator. What do you think a lot of people do wrong when they put this in the calculator? Well, let me start right.
Any of them in brackets?
Yeah, what do you think needs to be in brackets, Elizabeth? What's wrong? What's wrong with this, Elizabeth? What's wrong with what I just wrote up here?
Nothing.
Okay, so this is important. I'm glad we're having this conversation. When you write this in the calculator, here's what the calculator thinks you want. Right? Because it's going to do the order of operations. It's going to do multiplication and division from left to right. It's going to do 3 divided by 2, and then it's going to do times pi times inverse cosine of 0.6. The calculator won't know that the pi is part of the denominator unless you tell it. So on your calculator, you're going to need to tell it that pi is part of the denominator if you want it to do what you're asking it to do, or what you thought you were asking it to do. All right, and just to make sure, let's go ahead and put that in. 3 divided by parentheses 2 pi inverse cosine 0.6, and we're getting 0.443 to 3 decimal places, anyways. All right. So but this says to the nearest tenth of a minute. So to the nearest tenth, 0.4 minutes. And this is actually what I got from estimating from the graph. So if this is 0.4, I know this third time is 3.4 minutes. What's this one right here? You're in the right ballpark, Charusa. This is something that
2.7.
this is something a lot of you guys had trouble with the first time. Look, this distance from here to here, right, from the time we're at 10 feet to get to 20 feet, should be the same time it takes to get from 20 feet to 10 feet, shouldn't it?
Oh, 2.6. I did.
Yeah. Yep. So if this distance from here to here, if this takes 0.4 seconds to get from 10 feet to 20 feet, then it's going to take 0.4 seconds to get from 20 feet down to 10 feet. And 3 minus 0.4 is going to be 2.6. And then that means this fourth time is going to be exactly 1 period later, 3 minutes later. That's going to be 5.6 minutes. All right. And a lot of times, a teacher goes over this stuff, make it feel real easy, and nobody else is asking questions, so you're like, oh, I must be the only one who's not getting it. But until it really registers, it's not easy. So if you're still not getting it, please, now's the time to ask questions, because tomorrow I won't be able to answer too much when you're actually taking the test. People feel okay with this?
Yeah.
Anybody want to ask to repeat part of this? All right. Well, if you change your mind, you decide, hey, can we go back to number 10, start that over, or anything like that, let me know. All right, this one here, two populations, and if we're increasing by a percentage rate, we know that's an exponential function. The way I like to think of these is we're always starting with 100%, and if I grow by 8%, I'm going to have 108% of what I started off with, and that translates into 1.08 as a decimal. And this one's decreasing, so if I had 100% and I lost 5%, each year I'm going to have 95% of what I started off with the year before, and that translates into 0.95. And you have the option of just calling this 30 and letting it represent thousands, but let's just keep the zeros here. C of t equals 30,000 times 1.08 to the t power. And population D of t is 50,000 times 0.95 to the t power. So right now, population D is higher, but it's decreasing. Population C is lower, but it's increasing. So we can bet that sometime in the future, they will be equal, as long as these trends continue. All right, so let's go ahead and set them equal to each other, because that's what C is asking. When are these equal to each other? And we don't need all these zeros. In fact, if I was doing this for myself, I would just call it 3 and 5. And let's go ahead and do that now. Let's divide sides by 10,000 and make this easier to look at. And does anybody remember how to handle a situation like this? Do we want to take the log of both sides now? When you're finding an exponent, you generally want to use logarithms. Do I want to take the log of both sides now, or is there a better way to do it?
Divide by the 0.95t.
Yeah, I mean, you can take the log of both sides. you can do this. In fact, I've seen some teachers teach it this way. They'll say log of 3 plus t log 1.08 equals log of 5 plus t log 0.95. I'm personally not the biggest fan of that. I like to just combine the two bases, especially if they already have the same exponent. And if you're really comfortable with this, you'll divide both sides by 3 in the same step. Get the 3 under the 5. But because both of these numbers have the same exponent, I can make it one fraction with that exponent. 3 times this fraction to the t power equals 5. Now I'm going to divide both sides by 3. And then I'm going to be able to take the log of both sides. Whatever 1.08 divided by 0.95 is to the t power equals 5/3. And you don't want to call this, you don't want to turn this into a decimal, either one, because you're going to end up rounding off early and then taking the log of a rounded off number. So now we'll take the log of both sides. T times the log of this first fraction equals the log of this second fraction. Divide both sides by the log of the first fraction, and here's what we get. The log of 5/3 divided by the log of 1.08 over 0.95. And that's going to give us about 3.983, or 3.9 is fine, and t is years. So it doesn't take very long, relatively. And if we were going to plug that back in and find the actual population, the best idea is to just store that as x and plug it in as x, or something like that. Keep all your decimal places. Ramon, did we explain that one to your satisfaction?
Yeah, yeah. That.
Okay.
So basically, you'll do the decimals first, like get the decimals out of the way, and then when you have all the terms together, that's when you do the log of them.
Yeah, or when you get real comfortable with this, let me just give you a similar one. Let's say I had like 7 times 3 to the x equals 8 times 2 to the x. You can decide. You can say your thought process is, I want to combine the 2, get it under the 3, and I want to get the 7 under the 8. If you're comfortable enough with this, you can just go right to this. Or if you got the exponential stuff on the right side and the constants on the left side, you'd have this.
All right.
So you can do the log of 8/7 divided by the log of 3/2. Or that you get the same answer if you did the log of 7/8 divided by the log of 2/3.
Okay.
Okay.
That makes sense.
All right, good. All right, does anybody else have any questions or issues with this one? Again, if you change your mind, let me know. But let's go on to page 4 while we're in the meantime.
Mr. Shin?
Yes, sir.
Can you go back a little bit?
Of
I
course.
forgot to take a picture.
Sure. This one?
Yeah, on top.
So you want to...
Yeah.
Is that high enough, or keep going?
It's good.
Okay.
Good. Thank you.
Pleasure. Okay, so anytime I'd ask you to use a compound interest formula, I'd give you the formula. I might not remind you what everything stands for, but because we've used it a few times. Not too many of you, but a few of you forgot on the last test to turn that into a decimal. Make sure you understand in both the compound interest formulas, when you give the rate, you always convert it into a decimal. You divide by 100, move the decimal 2 places to the left, however you want to look at it. And the doubling time, the shortcut to solving this is just this. But it comes from, I'm starting off with a certain amount of money. I'm earning continuously compounded interest, and the rate is 3.5% per year. I want to double my money. But when I divide both sides by the original amount, it turns into this. All right? And I like to look at this as rewriting the equation, but you can look at it as taking the natural log of both sides. I take the natural log of the left side, and when I put a ln in front of the right side, it cancels out the e. But I like to look at it as just converting from exponential to logarithmic form. The log equals the exponent. And now natural log of 2 divided by the interest rate gives me the doubling time. It's usually about 19 or 20 years. 19.804 years. In fact, I think that might have been the same problem that was on the last test. Yeah, so the last test, somebody told me they couldn't see their score, and I went and did, I clicked on something, and I undid all my corrections on the on Edge Elastic, and then I went to go fix it, and I realized it had wiped out people's text answer, and I was like, you know what, I'm not going to be able to fix this, but I already had the scores, and most of you had already seen your scores. I'll make sure I don't make that same mistake on the final. And I'm not going to disappear and hide if you're having trouble seeing your final exam score after you take it. Just get in touch with me, text me or email me, and I'll send you your score. And I can even tell you what problems you had trouble with if you want me to. All right, and we started off the very first day solving some right triangles, and there's one place that right triangle trig comes up on in AP Calc, and it's a topic called related rates. There's quite a few related rates problems that involve right triangles. So it's good to have brushed up on it. It seemed like it was old news for everybody, and everybody was pretty good at it. So hopefully that's still the case. There's one of these things I don't need any trigonometry for, and that's finding the hypotenuse. B is just going to be the square root of 25 plus 9, right, by Pythagorean theorem. And so that's the square root of 34. And if it asks me to give it as a decimal, it says to the nearest tenth. So square root of 34 is about 5.8 to the nearest tenth. I believe we asked for angles to the nearest degree. Now, for me as a teacher, if I asked for 1 decimal place and you give me more accuracy than I ask for, no problems. But, know your teachers. Some teachers, if they ask you for 1 decimal place and you give them 2, they'll be like, you didn't follow my instructions. But for me, if you give me less than I asked for, then I'd take off points for that. If you give me more than I asked for, no issues. And angle A or angle C, I want to pick one to find, and to find angles, we need inverse trig functions. So I'm going to start with angle A, 3 is my opposite. 5 is my adjacent. So that's a tangent equation. Tangent of angle A equals 3/5. A equals the inverse tangent of 3/5. And some people look at this as taking the inverse tangent of both sides. On the left side, inverse tangent cancels out tangent. On the right side, I get inverse tangent of 3/5. We're rewriting it any way you look at it. And inverse tangent. And by the way, on this one, we want to be in degrees. So when you get to that last page of your test, go ahead and change your mode to degrees. Because it does say to the nearest degree. Inverse tangent of 3/5 to the nearest degree is 31 degrees. Right, it's 30.9, but I will honor that, idea of you can round or truncate, so you could say 30 or 31. But if you say 31, then you've got to say 59 down here, right? Because your two acute angles have to add up to 90 degrees. So 90 minus 31. If you call this top one 30, then you better call angle C 60. You can also do inverse tangent of 5/3 if it makes you feel good, but you can just subtract from 90. Any questions on this one? These looked pretty good on the homeworks that were turned in. Yeah.
I got last time 30.96.
Yeah. So yeah, you're right. So first of all, if this were an AP class, they wouldn't let you do to the nearest degree. They always want 3 decimal places on everything. But if somebody asks you but their rules are, Cheruza, that you can either do what's called truncating or follow the traditional rules of rounding. So traditional rules of rounding say that after the decimal, if there's a 5 or higher, you round up. But truncating means you just chop it off. You ignore everything after the decimal. So I would accept, on this, I would accept 30 degrees or 31 degrees. Am I answering your question, or am I missing your point?
Yes, sir.
Okay.
Your answer.
All right, good. And so for angle C, if you called angle A 30 degrees, then you need to call angle C 60 degrees. You following me on that?
Mm-hmm.
Beautiful. All right, any other comments or questions on this one? All right. So let's do one more. So I've got to pick one of these that I want to find first. I'm going to find A first, and with respect to this angle, A is opposite. The 12.3 is adjacent. Tangent of 35 equals A over 12.3. I'm going to multiply both sides by 12.3 and put it in my calculator. 8.6 to the nearest tenth. All right. And a comment I meant to make up on this one up here, when you're finding the angles, I'll go back for anybody that didn't get, don't use the 5.8 when you're finding A or C, because the 5.8 is a rounded off number. You're best off using the exact numbers that you started off the problem with. So even though I could have said inverse cosine of 5 over 5.8, I don't want to do that because the 5.8 isn't exactly 100% accurate. All right, now angle B, or side B rather, B is the hypotenuse. And again, I don't want to say 12.3 squared plus 8.6 squared equals B squared. I don't want to use Pythagorean theorem because this is rounded off. It's not an exact value. I'm far better off just using a cosine equation. Cosine 35 degrees equals adjacent over hypotenuse. Final answer is 12.3 divided by cosine 35. And if anybody needs a reminder, it's because we cancel out the denominator and then we divide by the cosine of 35. In order to get b by itself. And that's going to give us to the nearest tenth 15.0. And you could say 15 if you wanted to.
Can you move the page down? I wanted to take a picture of the previous problem.
Sure, sure. Is this far enough, Victoria?
Yeah.
Okay.
I'm taking it, thank you.
Sure, sure. Anybody else have anything on these 2 pages that you'd like to go back over or talk about? All right, why don't we talk about the first page a little bit, and then we'll, Mr. Kaplan, if you'd like to try again to show us what he was going to show us yesterday. So why don't I actually open up the answer key on this one. Well, actually, I don't need to do that. I'm going to do a different screen share, though. Let's get the calculator out. Yeah.
I was confused about the x equals 2, so.
Yep.
I thought the variable was t, so then what does that x stand for?
Yeah, you were asking about this same issue yesterday. So let me show you. Let's take a look at the graph, and I'll try to answer that question while we're taking a look at the graph. Okay.
Okay.
So let me go to my browser here. Actually, let's go to desktop, so I can switch back and forth easier. Okay. Let's go to. Okay. Get this out of the way. So I'm going to out some of these problems. This, remember, anything until the right triangle, you want to be in radian. I just wiped it out. Was it 1?
Sine.
Yep. Plus 2 sine, right? Wasn't it? Of t squared over. Can somebody come out? Was it x squared over?
Was it t squared too?
Thank you. On your calculator, you have to put x. All right. So, first of all, we're concerned. First couple of questions. This first question is asking about on the interval 0 to 3, but right here I say it's talking about v of 4. So let's go back, set a window. I can my midline is highest is going to be 3, lowest is going to be negative. So setting my y and y is going to be easy. -1 my y min, 3 for my y min. We leave it on 0 to 6 for x. So I'm going to go look at my. All right. So Mark says that at t2, particle. I'm sorry. At t equals 4, right? The particle's at x equals 2. Okay.
I know that's confusing. Though.
Yeah. Yep. So let me go back here. So my cursor is.
Mm-hmm.
I'm at on the x-axis. All right, and I think I might have.
You're at, aren't you?
Thank you. Okay, equals 4. Thank you. Right, 2 on the x-axis.
Wait, what?
Yep. Now the value is my velocity. Velocity is 2, but on the x, I'm at 2. You have to imagine just a speck on this. At t equals speck is at 2. Now velocity is positive, so I'm traveling to the right. I'm traveling to the right. Now I turn around. Now I'm traveling to the left. I turn around. I'm traveling to the right. Where velocity is positive, I'm traveling to the. Here I'm traveling to the right quickly, to the right slowly. Here I'm traveling right slowly. Traveling to the left quickly. Here I'm traveling left slowly. Traveling to the left slowly. Right? It's a tough thing to get around, but if right here t equals 4, I know it goes at 2 on the x-axis. It's going towards 3 and maybe 3. We don't have the unit problem of the.
Wait, so then be the variable or is this the variable?
Well, there's multiple things that we're keeping track of here. We don't have it, but there's position function, right? We don't have equation of the position function. In calculus, you'll learn to figure out the position function based on, what information you've got here. At least, sometimes algebraically, sometimes circularly. But we don't position function, but all about position is right it's at 2. Because the velocity, it's traveling. Now it's to the right. It's continuing to the right. Continues to move to the right. Stops for an instant, it's a split instant, and now we're back towards 2. Back to the left, back to the left. Stops for an instant, now it's going right, to the right, to the right, to the right.
Could I interrupt for just a second?
Yeah, please.
Lucky I'm able to share screens. There's one that might help with this. So
all right, so let me
when I get to that, I'll point it out, but we don't have to do it now. But
okay.
I'll point it out when we get there.
So did you want to say something now?
Just wanted to say maybe Mark should
okay. All right, so
wait and I show the screen.
Sounds good. All right, thank you. So yeah, we'll to that in just a minute. Stop the share, guys. I'm sorry. About stop the share, and then I did it. Back to the graph. Anyways, what is V of 4? You guys are good at that. You plug 4 in. It tells you at t equals 4, such and such is the velocity of the particle. And if you wanted to say because it's positive, you can say it's traveling to the right. At t equals 4, the particle's on the positive side of the x-axis. And I wrote a little comment that I didn't need to write because it tells you the answer up here. At t equals 4, x equals 2 is on the positive side of the x-axis. All right, I was thinking of something. My head was in a different place. So the little comment that I wrote down here on the answer key, it's pertinent to some problems, but it was unnecessary for this one. And it's moving to the right because you got a positive value here. All right, sketching the graph on the interval 0 to 3, all we have to do go from 0 to 3, copy on, just put some units, just, here, I guess it's just right from the x, right, the y-axis and negative, and make it look like the high 4t equals 2, and then you've got a good graph. All right, so moving down here, when does it change direction? When's it moving left and when's it moving right? Well, it changes direction here, moving to the right from 0 point something to the left point something. And I saw a couple that seemed to use the arrow feature on their calc, people that hadn't understood the answer to the rest of it, but hammer. So I'd like to show you how to find a 0 now. And I'm going to give you a calculator with you. Take a minute and put into y equals. I'm going to show you how to find 0 on the calculator if you don't know how to do that. Velocity change sign, that's when you change direction. From moving to the right, moving to the left, or vice versa. I'm going to go to window and set up this window. Did I go on too fast? For a second, are you still set, buddy?
Hold up.
Okay, sure.
Okay, got it.
Okay, anybody else? All right, let's go. Just make sure you're seeing what you go on, because I forgot what's wrong. Anybody want me to? All right. What is this cross the x? And just like find the maximum, to find a maximum, I'd let look between x equals 1 and 3, and I'd have like 2.9. If I want to find a 0, I need to look in here. A cross x-axis between 3. So everything good is here. Set trace, and I want to pick 0. So I can go down with the arrow and hit the button 2, and left bound. Now I use arrows if I want to, but I know 2 and 3, so I'm going to type 2, enter as bound. Just like for a maximum here. Look in here. And my bounds. It's 3. So I'm going to 3. I can't see the marker here because it's editing, but it's looking between the edge of my screen. And I guess you can type in it or just hit enter. I'm going to hit enter. And there's where we cross the x's at x 2.70.
Oh, yeah.
Would anybody like me to run through that again?
Yeah.
All right. So it goes like this. Second trace. Pick number 2. Now, I can see the x-axis between 3. So 2 is going to be my left bound. Is left bound question type 2. I think let me try this again. 2, and then it says round. I'm going to type in 3, enter. And this guess, you can hit enter. This time I'm going to 8 and see if it's different than I got the first. Same answer this time. So 3 guesses, it will always be the same. Depending on the fin and the size of your ink, it could make a slight difference. Should I run? Sometimes it's a good idea to show you more than one thing. Sometimes it's a bad idea. People are trying to get the hang of the first. It's kind of a cool show you a little trick that I learned from De Gutierrez. He's one of the instructors of the other sections. Use the 0 feet. He does this. He goes, and if he wants to know, he just y equals 0 in as a section. This is the intersect feet. So you see the second graph, the x-axis, and he just goes second, intersect, enter, and enter. See his way takes a little long, but we get the same result. I personally, I'm comfortable with the 0 feature. I think he feels like it's easier for us to do it this way. Whichever way you look, gives the same result.
Session?
Yes, sir.
Yeah, yesterday I didn't have a calculator with the we got the equation, then we equate it to 0.
Mm-hmm.
Then solve. Then when we reach the sign, we look for sign where is the negative half on the unit circle.
Yes.
Then we get all the value. Then we just pick the answer which has the because remember they say should be in between of 0 to 3.
Yep.
So we just got a value. We got four values. Then between those 4 values, we just pick one which was between 0 and the 3, and we got the same as 7.
Yeah, the problem that did yesterday, I think was a no calculator problem. We didn't need a calculator. As far as the test goes through, you won't need any graphing calculator feats. Anything you on the test, a scientific calculator is good enough for. Although, any that's going to be an AP calc, it can manage a TI graph calculator is a good investment. You'll use it for the rest of high school and into college too. It's a wild investment if you're able to make it. Not cheap though. That even
Yeah, I'm gonna have one.
Even a 83, if you can still find them, that they're going to charge you close to $90. Once in a while, I get used one on Amazon for better money, but
I got one on this list, and also this week Staples has a sale. I think the 84 CE is $99, which is a lot of money, but it's less than the usual price.
All right, let's go back to this question here. So 2.707 is when it changes direction at t equals 2.707, and you want to write, and I wrote this on the answer key, so I'm not going to continue all this, but you definitely want to write because v of t changes sign. All right, when is it moving to the left and when is it moving to the right? It's moving to the left from 2.707 to 3 because v of t is less than 0. Here is where it's moving. Say that it's moving to the right from 0 to 2.707 because v of t is greater than 0. Right? The average rate of change in v of t. You want to calculate the slope between the points at t equals 0 and t equals 3. So you want to basically calculate this, and that will give you the average acceleration on that interval. And you can calculate that to y1 parentheses y1 3 minus of z by 3, right? Negative 0.2, and if velocity was in meters per second, this would be meters per second squared. But that's the average from 0 to t equals 3. That's the answer I want to give. And on the interval 0 to 10, I saw 1 or 2 people had the correct answer, which is 16 times. One person had 15 times. So let's just look at that together. All I have to do to answer this question is change from 0 to 10. Keep track here. If I cross the x-axis side, as long as I'm changing direction. 1, 2, 4, 5, 6, 8, 9, 10, 11, 15, 16. Not sure about this last one. You can go investigate between 9 and does cross 4 times 9 and 10. And one said, because is time between 0 and 3, then it must cross 3 times between 10. If this was periodic, putting the x squared in changes the waves as you go forward. So it's not a periodic function, or even though it involves a sign. All right. Does anybody have anything they want to ask about on this before I turn it over to Mr. Kaplan? All right, let me stop my screen share here and turn it over to Mr. C.
Okay. All right. I've set up what I think is a show of the things I wanted to show yesterday. And also one of these has something that I think will help Mark and other people understand what's going on. I'm going to try to share my screen and see what happens here. First push their screen. And then push this. Okay, can you see that graph?
Not yet, no.
No? Okay. All right, well, let me do this again here. Oh, I have to push share again. Okay, let's try this. How about now?
Yes.
Okay, let's go over here. All right, this is a mass on a spring bouncing up and down. That's called simple harmonic motion. And I think the other day we had one of these where there wasn't a t squared, just a t in the sine term.
Mm-hmm.
And that would describe this motion. Now, here's another example of simple harmonic motion, pendulum. And here's another example. This one I want to show you because someone was kind enough to actually write this program for me. Here's the program. It's pretty simple. It looks simple, let's put it that way. It's done in Python and something called GlowScript. So let's see if we can get it to run. Yeah, so there's a pendulum going back and forth, and there's the angle being plotted. And I think when it gets to about 10 cycles, it'll stop. And that looks like a sine wave. I think it's very, very close, but for a pendulum, unless the the swing is very small. It's not exactly a sine wave, but let's not worry about that. Okay, now this one, this is the important one. This has two parts. I'll show you the first part. There's an actual picture of a spring, and don't worry, the graph on the left is very interesting, but I don't think we need to worry about that. But the one on the right is showing you the position as the mass moves up and down. You can see it's a sine wave, and we can step through it, and it's showing you the position. Now, the graph that Mr. Sheehan had just a few minutes ago was velocity, not position, but this is the position, and they call it y here because it goes up and down. So this is a graph of position versus time. Now, the very interesting thing about this is, you see that I scrolled down? Well, I guess you did. I didn't hear anything.
Yes, I'm sorry. Yes, we see.
Okay. Okay. This one shows three things, and I think this sort of answers Mark's question. The graph that Mr. Sheehan had just a few minutes ago was one of velocity versus time, but here's position and here's acceleration. And it turns out because of, well, the calculus tells you very simply that one is the derivative of the other is the derivative of the other. Once you know calculus, it's very straightforward. But the point is, the graph that you had in the last problem was velocity, but you could have had a graph for position versus time, but you didn't. So now I'm going to start this going. It's a little hard to understand without knowing all the physics, but just watch. The top one is position, and you can see it follows where the mass is, but the middle one is velocity, and it gets to maximum, I think. Let's see if I can stop it near the middle. Actually, let me step through it. Okay, at the middle, the velocity has the highest magnitude, because if you think about it, at the ends, the position is farthest from the middle, but in the middle it's going fastest, but it turns out mathematically it has no acceleration in the middle, just for an instant. So we'll step through it again. So now here we have maximum position, that's one end. Well, almost, it doesn't let me, but we have zero velocity, but we have maximum acceleration. So I don't know if this helps Mark, but here are three different graphs of three different things. This is, they call it Y, but you would have called it X in that other problem. So this is the position of the mass as a function of time. This is the velocity of the mass as a function of time. And this is the acceleration of the mass as a function of time.
Yeah, he could.
And
could I just make a comment? Like, this is a great tool here. Let me see if I can write on this, because this is, you're right. This is really going to help Mark. So can you see my cursor, Mark?
Is that one yours? The one that's like,
yeah. Mine's the black one. Yeah. So look here. This is velocity, right? The whole time this is positive, which is right up till here. This is moving up or to the right if it was horizontal. This whole time where velocity is negative, this is moving down. Do you see that? Or to the left, right? The top one's position. Then this whole time when velocity's positive, this is moving up or to the right. Is that a little bit easier to understand, Mark?
yeah.
I mean, it's a great.
Wait, I have a question.
Yeah.
So basically, is the position at where for that velocity? So let's say, like the other problem, it said x equals 2 at t equals 4. That means that x equals 4, the velocity is 4, or I think I confused the numbers, but.
Go ahead. Maybe Mr. Shane can show from these graphs.
Yeah,
but it's basically like the position at that velocity, or.
Yeah, so let's just say, so this isn't going to 100% fit with the problem, but let's say we had in our problem velocity was positive at t equals 4, and the position was positive, right? So let's say this is t equals 4. And let's say the y value here is 2. All right? Or let's say this is, instead of y, let's say this is position on the x-axis. Okay? And And now at t equals 4, my velocity is also positive.
Yeah.
Right? As long as my velocity continues to be positive, now I'm moving towards 3, right? Now I'm higher than 2. As soon as that velocity hits the x-axis, now I'm coming back towards 2. And if velocity, all right, so as long as velocity continues to be negative, I'm moving back to the left on the number line. And then once velocity returns to being positive, now this particle's moving to the right. 0, 1, 2. I'm not sure if that's helping, Ramon, but
It is.
I was attempting. Does anybody else have comments to make on this? Thank you, Mr. Kaplan. This was really a good idea.
Okay, there are a couple more.
Yeah,
First of all, let me just say,
please keep going.
That in math classes, they do this, as you've seen, in one problem. And then in physics class, we do this in about 6 or 8 weeks. So this is very important, and we spend much, much more time on it. So if you don't get all the details now, if you study physics, you will get them. And if you study calculus, I think you'll get them. But it's important to understand the problems that Mr. Sheehan has given you. But it goes on. In fact, let me just scroll down quickly. There's some calculus down here showing how to derive one of these from another using derivatives. So there's a lot to this. Okay, now if you don't mind, I'll move to the next
Please,
slide.
Yeah.
Is that okay?
This is great.
Okay, this is a picture of the Hancock building. And what they're showing here is that, I will show you on the next slide, but on the 58th floor, there's a 300,000 pound lead object that moves back and forth sometimes to try to prevent the building from swaying in the wind. And this was added after the building was built. And it's kind of a pendulum. And I'll show you in the next. I found out about this a long time ago, and I wanted to get a tour of this. And there was a professor at MIT who gave tours. And when I found out about it, was I think 2000, and he was in Florida for the summer. And he was going to give tours when he came back, but then there was 9/11. And after that, nobody got tours of any tall buildings unless you went through a, security check that took months or something. Anyway, I never got to see it. But here's some pictures of it. That big orange thing, I believe, is a 300,000 pound hunk of lead, at least on the inside. And I'll just run this video. Well, I don't think I'll run the video. If you want to see the video, I can send the link to Mr. Sheehan. But the electrician who takes care of this talks about it. And this thing just moves sometimes, only during certain seasons when the wind is right, to try to keep the building from swaying. So it's sort of a pendulum that's compensating for another pendulum.
Wow.
I find it very interesting. There's a lot of information on this on the web. If you look for, I think, maybe vibration dampers. Anyway, if you're interested, I can provide more information, but that's a picture of it. And if you go to this website, which I can give you the link for, the electrician talks about it, and you'll recognize that he's from Boston when you listen to how he talks. Just one more thing I want to show you, which is unrelated, but it's related to what happened to me yesterday. This is a graph, and the cooling curve is an exponential, and this heating curve we call it an exponential, but it's really 1 minus an exponential. And the reason I bring this up is that the power here went out last night at 10 past 8, and we have a generator which failed at 10 p.m. So the refrigerator wasn't running for many hours. And fortunately, it seems that we just left it closed and it's okay. But I was thinking this morning that here's where math sort of applies. You see, if the refrigerator is heating up, unfortunately for me, it heats up more quickly at the beginning when the power goes off because it's further away from room temperature. And that's bad because that means even if the power's off for only 2 hours, it's going to get somewhat warm. But I guess the good news is that toward the end, it takes a longer time to get to room temperature. But I just wanted to show you this because these are, we call this one an exponential. This one, it really is an exponential. This one is 1 minus an exponential. And just one more thing about this. I've done this in the lab at Wellesley, the cooling part. I heated up some water. I had an electronic thermometer that I put in the water and let it cool, and I think it took over an hour from what I remember. No, more than an hour, several hours, but I got an exponential curve and I could fit the equation to it, and it was just right out of the textbook. So this is just another example of this stuff in real life. And while I'm speaking, this is important. This exponential decay is really important. But that simple harmonic motion, people spend semesters studying that, and engineers spend their careers studying vibrations. So this is very important material uh, uh, in many, many ways. So that's all I have to say for now. If Mr. Sheehan wants, I can send him these links, and then he can provide them to the rest of you, so you can
That'd
look
be
at
great.
these in
Sure,
more
sure.
detail. Especially the Hancock building. That's interesting, but the video takes a few minutes.
Yeah, I didn't know about that. Thank you. And I do remember when they first built that tower, when the panes of glass were falling down on the street.
Yeah, I think that was a different problem. I think that had to do with the wind currents. And one of the things they mentioned, let me just see, I'm going to go back here and see. I think they mentioned it here that, let's see. Okay, well, a famous example. Well, I don't know if I see it right here, but when the building was built, I think they made some mistakes, but also it was built in 1968 to 7. Well, I'm not sure just when, but people knew less about this then. They started learning about it when it happened with the Hancock, but they were surprised. And there's also a picture. There's a bridge that collapsed. Well, you could look at it. I think it was called Galloping Gertie in the state of Washington. That it just started oscillating and the bridge collapsed. There are movies of that, and nobody had any idea that would happen until it happened. And then the engineers went back and had to analyze why. It wasn't that they made a mistake; they just never even encountered that kind of problem before.
Yeah, I could see on your screen here that it says there was a faulty window seal system, and that's why the windows blew out.
Yeah, there was. Yeah, I would just add that my former brother-in-law is an architect, and if you see the name I.M. Pei here, he says what they say is if you deal with I.M. Pei, it's I am and you pay.
Yeah.
Okay, now I'm going to stop sharing, and then I guess it's back to Mr. Sheehan.
Beautiful, beautiful. Thank you for that. All right, so I have a couple of different ways we can go, guys. I have brought a couple of things to do, but first of all, if there's any review you want to discuss, now's the time to discuss it. Tomorrow, I'm just going to put you on Edge Elastic, and you can have the whole class time to work on the final. Hopefully, you won't need the whole class time, but you'll have it. And before anybody leaves, I want to say I've really enjoyed this, and I wish you guys all the best of luck. If anybody needs a letter of reference, if you think I can help you with that, contact me during the year. If you have math questions during the year, I'm more than happy to help you out. But hope you guys have enjoyed this, and I definitely have this summer. Some of you I can't see your face, but I know your voice, and I kind of get to know you by your work, and I've enjoyed that. Does anybody have any review they want to talk about before we just go on to some extra stuff? All right, I've got a couple of options. I brought some more modified AP questions, and I have a whole set that involve trig functions. So we could do that. I also have a set of AP question, like an unmodified AP questions where they're kind of algebra heavy. Does anybody have a preference? You want to do the trig functions, or do you want to see some algebra that involves logs and or exponential functions?
A little of both.
A little of both. All right. Let's see. All right, we can get a little bit into both of them. Sure, we won't get heavy into either one, but all right, fair enough. Let me get this ready on my open board here. Let's start off with the algebra problems. And now I don't have the full question on a lot of these, but these are equations that came up on actual AP tests. I taught AP Calc a number of years, and I pulled these together for use in bridge to calculus, just to show people um, that you'll actually use this stuff that you're learning. So share my screen here, desktop. Yeah. Okay. Okay, hold on. Okay. There we go. Okay, so basically what you had to do is, so these came up like, find when the particle changes direction or something, and so you had a velocity, and you had to set it equal to 0 and see when it changes sign, or sometimes they represent different things. Position, velocity, acceleration are big ones, but there's a lot of instances in calculus where you have to figure out where something changes sign. All right, and so here's some algebra heavy ones. I'll do a couple of them. If you tell me you want to try a couple on your own, I'll let you try a couple on your own. Otherwise, we'll move on and show you something else. So let's take number 4 here. I want to know, when does f of x equal 0, basically. A root for an equation is where the equation equals 0. It should probably say the zeros for the given function. When we talk about a function, we usually say zeros. If there's only one variable and it's set equal to 0, we usually use the word roots. This should probably say zeros because they're functions. But anyways, I want to set it equal to 0, and I want to try to factor it, because otherwise I'm going to have to use a graphing calculator. And these are all factorable. All right, the obvious thing is here, both of these terms have e to the x in common. So I'm going to factor out e to the x. And can anybody tell me what goes in the parentheses if I factor out e to the x?
X squared plus 4x minus 1.
Okay, you're taking it. You're pretty comfortable with this. For anybody that's not, so the first term has this times e to the x, and the second term has this times e to the x. So yeah, Mark is able to take the next step in his head, but here's where his first step was. He just had already taken the next step. Are people seeing this okay? We're not really viewing this as separate parentheses, but we're basically doing the same thing as if I had, like, 5 e to the x plus e to the x times 2. I'd say it's e to the x times 5 plus 2. But instead of a 5 and a 2, I've got, a trinomial and a binomial. All right, and you can see those yellow brackets are not necessary. So let's combine like terms. X squared, 2x plus 2x gives me 4x. And then negative 3 plus the 2 gives me negative 1. All right. And this is not the best example to start off with, because we cannot factor x squared plus 4x minus 1. But the idea here is I've got a factor times a factor equals 0. So either this factor or this factor equals 0. And what's important to understand, and you'll run into this a few times in AP Calc, e to the x cannot equal 0. It's always positive. So I don't have to worry about that. I can focus on x squared plus 4x minus 1 equals 0. And this one's going to need some quadratic formula. So negative 4 plus or minus, this is going to be 16 plus 4 square root of 20 over 2. That's negative 4 plus or minus 2 root 5 over 2. I don't think I've ever seen an AP Calc problem where you had to do quadratic formula for what that's worth. So anyways, I'd have two zeros for this function. One of them would be negative 2 minus the square root of 5, which is clearly negative, right? And the other one would be negative 2 plus the square root of 5. And since square root of 5 is a little bigger than 2, I know negative 2 plus the square root of 5 is positive. All right? So when you're making a sign chart, I just want to know, well, actually, I found the zeros. I'm not making a sign chart. I'm thinking of the next set of problems. So anyways, those are my two zeros for the given function. They're negative 2 plus the square root of 5 and negative 2 minus the square root of 5. Those are my two.
So you wouldn't use like calculus at all in this? You just use like algebra?
Yeah, no. So depending on what this equation stood for, there might be a calculus idea in here. Like, so if f of x represented velocity, you'd say, you know, your particle changes direction at negative 2. Well, actually, you'd have to determine that it changes sign. So you'd actually have to do your sign chart, see where it's positive or negative. But where the, you know, if velocity is 0 at these 2 points. All right, or the position of something 0. There's lots of different kinds of things that could come up.
Would the student be allowed to do what you did earlier, using the graphing calculator to find the zeros?
Sometimes yes, sometimes no. There's a non-calculator section of the AP test and a calculator allowed section of the AP test, and on the calculator allowed, you'll find a few problems where you don't need the calculator, but there are plenty of them where you're going to need to use features like the intersect feature or the zero feature or the maximum minimum feature of the calculator. All right, let's do one more here together, and let's try this one. All right, number 6. All right, we've got a 2. All right, if I'm going to set this equal to 0, I really don't care about the 2. Right? I can divide both sides by 2 and not pay attention to it. What can I factor out of both terms? How about somebody who hasn't spoken up yet? Can somebody tell me what, if I think of this as, if you've seen it like I do, this term and this term, what do they both have?
E to the negative t.
And
1.
And a negative 1. So let's factor out a negative 1 e to the negative t. And I have to have 2 terms left inside. What would I put first? E to the negative t times what gives me this?
1.
1, good. All right, now plus e to the negative t times what gives me all this?
One minus t.
Good, 1 minus t. All right, now let's combine like terms. Negative e to the negative t times 2 minus t equals 0. This can't equal 0. All right, because e to the t can't equal 0, so e to the negative t can't equal 0. No power of a positive number can be 0, even if you multiply it by negative 1, or, you know, it doesn't matter what your exponent is. this can equal 0 when t equals 2. So there's 1, 0 for this function, and it's t equals 2. Let me show you one more type of thing that's related to this, and then I'll let you guys decide, do you want to try a few of these on your own, or you want to just keep looking at stuff. That's not what I'm looking for. Looking for my controls here. Hold on a second. I don't know where all my controls went. Interesting.
Is it the left side, like that tab with that arrow?
Yeah, no, I was looking at that.
Or is it the right side?
Oh, there it is.
I don't know.
Thanks, Ramon. Okay. So these are inequalities. So I want to know, when is the function less than 0? Or when is the function greater than 0? So I have to find the zeros, and then I also have to do a sign chart. And this is the type of question, somebody might ask if these represented velocity, when is the particle changing direction? That might be something related to what we've been talking about that might come up. So let's take something that's similar to what we were just talking about here. This is a little bit tricky. And first of all, I don't like this negative as my first term if I don't have it here. So actually, it doesn't matter. So what can I factor out? What do both of these terms have in common? All right, not getting a response. Let me back up. If I want to know where's the function less than or equal to 0, I have to start with finding where's it equal to 0. So I want to set this equal to 0, and then we'll worry about where is it negative and positive. But if I'm looking at these as two terms, I see an overall term plus a term. What can I take out of the two terms?
E to the negative x.
E to the negative x, good. So I'm going to take out e to the negative x. And what's going to be left, I'm going to have a negative and an x squared plus 1. I can distribute it now, but just in the interest of being obvious, I'm going to do that. And if I take away the e to the negative x from the second term, I'm going to have a 2x. And I want to set this equal to 0. All right, so that's e to the negative x. And if I simplify everything inside, I'm going to have a negative x squared, a positive 2x, and then negative 1. And I'm not a big fan of a negative first term. So what I'm going to do, I'm going to put a negative outside. And let me know if you're not following this. But I'm going to multiply this first term by negative 1 and the second term by negative 1, just to make it easier to think about in a factoring. Are people with that step or no?
Yes.
All right. So now, this first term cannot equal 0. All right. Any power of e can't be 0. So I really don't have to pay attention to it. And this inside is very easy to factor. It's just x minus 1 squared. All right, so I want to know where does this less than or equal to 0 on this interval. All right, so it's really the negative 4s aren't too important towards the sign chart, but positive 1, right, is where the function equals 0. And I want to just basically determine what's it doing on either side. All right. The reason I didn't stop writing the negative e to the negative x is because it's gonna affect how this sign chart comes out. All right. I'm not going to think about the negative 4 and the positive 4 for a minute. Let's pick a number less than 1 and plug it in to this function. let's think of 0. 0 is an easy number. If I plug in 0, what's negative e to the 0? Positive or negative?
-1.
Yeah, it's negative 1. Anything to the 0 is 1. This is negative 1. So I get negative, and 0 minus 1 is negative, and 0 minus 1 is negative again. So negative times negative times negative, negative. Any number I plug in lower than 1 is going to give me a negative answer. Now let's try something bigger than 1. How about 2? E to the negative 2 is positive, but I've got a negative in front, so I'm going to get negative. And 2 minus 1 is positive, and 2 minus 1 is positive. Negative times positive is negative again. And we kind of should have known that. We've got this double root at x equals 1, so it should be the same sign on either side. My graph should bounce off at x equals 1. All right. So now let's think about this. To answer this question correctly, on this interval, -4 to +4, right? So basically, -4 to +4. When is my function less than or equal to 0? Anywhere except for +1. It's negative on the interval -4 to 1, not including, and, or union, +1 to +4. See how we're doing on time. How do you guys feel? You want to try a couple of these, or do you want to move on and see a couple more things before our time's up?
Can we try some?
All right. How about, let me give you one of these to try, since it's kind of related to the other examples. How about we take 10 minutes and try, how about number 9, and let's try number 11. If you're fast, try 9, 11, and 12. And I won't break you up into groups. Let's just take 10 minutes and speak up if you have a question, if you want to clarify anything or know if you're starting off correctly.
Mr. Shane,
Yeah.
so for question 9, after I think factorizing, right?
Yep.
Is that when we're going to find the value for x, or?
Yeah. So when you factor this, you'll realize that the first part, 2e to the 2x, can't be 0. So you'll figure out what makes the brackets equal 0, right? And then you'll set up a sign chart for f of x, right? And you should just have 1, 0, and you're gonna just figure out, is it positive or negative on each side of that number. All right, and if it's negative before the 0, you say when x is less than such and such. If it's negative afterwards, you're looking for y to be negative. Is that enough to go on, or should we get a little more specifically into it? Not sure. Give me, if you, yeah, take a minute, see if you're getting somewhere with it. If you're still not getting somewhere with it, let me know. And for anybody that's on it, number 11, if you're on a roll, then don't pay attention. If you're stuck, here's a suggested first step. How about factoring out a e to the negative x times x minus 1 and seeing what happens there.
I'm confused.
All right. So let's start going over number 9 together. Were you able to figure out what goes in the brackets in number 9, Victoria?
Oh, I started with 11.
Okay. All right. So you're taking on the tough one, huh? Does anybody want me to hold off talking about number 11? I tell you what. Let's hold off. I'd said 10 minutes. Let's there's 4 more minutes. But I don't want to leave you hanging by the same token. So Elizabeth, I'm sorry, Victoria. I'm suggesting taking out an e to the negative x and an x minus 1. All right. So if you look at this term, what's left if I take out the e to the negative x and the x minus 1?
Oh, true.
And this
Negative.
negative, right? So negative 2 goes here. Plus what? What's left if I take out a e to the negative x and an x minus 1? What's left?
Nothing.
Well, hold on. Remember, x minus 1 squared means I've got 2x minus 1s.
Oh, yeah. So that means x minus 1.
That's right. It's x minus 1. Bless you.
Thank you. I think I got it. Would there be 3?
Yep, 3 is one of your zeros, and what's the other one?
+1.
Yeah, good. Nice job. So 1 and 3 would be your two zeros. Clean up this mess a little bit. All right, why don't we start going over these? So number 9, we're taking away a 2e to the 2x from both terms. That leaves us 2x plus 1. This first factor cannot equal 0. 2x plus 1 can equal 0 if x is negative 1/2. So I'm making a sign chart for f, and I know it's going to be positive on one side and negative on the other side. So I'm gonna pick a number less than negative 1/2. All right, I'm going to test negative 1. All right, so if I test negative 1, well, 2e to the negative 2. E to anything is positive. Positive times positive is positive.
+.
Yep. And 2 times negative 1 plus 1 would be negative. That's negative. All right. Now, because there's no square on this, it's not going to be the same on the other side, but let's just take a minute. It's really easy. Let's test 0. 0 is on the other side of negative 1/2. E to the 0 is positive. 2 times positive is positive. 2 times 0 plus 1 is positive. Positive. And to finish up the problem, find values of x for which the function is negative. X has to be less than negative 1/2. That's the solution set to number 9. Number 11, here's the factoring. If I'm taking out an e to the negative x and an x minus 1, that basically leaves us the negative 2 from the first term, and it leaves us an x minus 1 from the second term. So if I rewrite this, here's what we've got. E to the next is always positive. X minus 1 can equal 0 if x is 1, and x minus 3 can equal 0 if x is 3. All right, so let's just make a little sign chart for function g, and let's test a number less than 1. Let's test 0. Well, e to the 0 is positive. 0 minus 1 is negative. 0 minus 3 is negative. Positive times negative times negative, positive. If I want to test 2, something in between 1 and 3, e to the negative 2 is positive. 2 minus 1 is positive. 2 minus 3 is negative. Positive times negative is negative. And if I'm going to test something bigger than 3, e to anything is positive. 4 minus 1 is positive. 4 minus 3 is positive. Positive times positive is, of course, positive. And this one is asking me, on the interval negative 4 to positive 4, where is the function positive? Well, it's positive between negative 4 and positive 1. So negative 4 included. 1 is not included. Comma or union. 3 is not included. Positive 4 is included. Okay. Did I lose anybody on these? And again, just take this, in the spirit that we're just trying to give you a little preview to some algebra-heavy things that might come up, but that involve some concepts we've talked about. Here's something I had here's real quick because I want to get you guys out of here. But here's a type of equation that comes up in a type of problem called separation of variables. We've got this equation here, and we want to find y. All right, so what cancels out? Ln, e. So here's one where I want to think of it as doing e to the left side and e to the right side. And what happens here? E and ln cancel out, and that absolute value of y minus 5. What happens here? I get, so this one here, I want to think of this as e to the natural log of x times e to the c. All right, because this e doesn't just cancel out the ln and leave x plus c, because the x plus c is not in parentheses. So I'm going to get x times e to the c, and let's just call e to the c is some constant. All right, let's call it d, which is a constant. If c is a constant, e to that number is a constant. All right, well, I've got an absolute value equation. So y minus 5 equals positive or negative x times d. And that's all I could figure out if I didn't have a specific point on the graph. But now I'm going to plug in negative 1 for y and 3 for x. All right, if I solve this, I get d equals negative 2. If I go down here and plug in negative 1 for y, and negative x, so negative 3d, I get negative 3d equals negative 6, which would give me d equals positive 2. So let's go plug it back in. So I'm going to add, so I'm going to take this equation, plug back in what I have. Y minus 5 equals negative 2d, which means y equals negative 2d plus 5. If I go plug in 2 for d here, I get, I still have a negative here. I get negative, y minus 5 equals negative x times 2, or negative 2x, and I get the same. What am I doing here? I'm sorry, it's not negative 2d. D is negative 2. It's negative 2x. I'm trying to hurry up here because I'm feeling you guys that need to get out and get on with your day. So either way, I get y equals negative 2x plus 5. All right. I'm sorry, Elizabeth, I didn't get to the AP questions, but if you like, I'll be happy to email them to you. But you can take a look, and a whole bunch of AP questions that I pulled together that have
thank you.
trig functions involved in them. Here's one. Here's a couple more. Negative 200 thirds, cosine 0.3. Here's one down here, 2 sine of t over 4. A whole bunch of them. And they're weird. They're weird variations of trig functions, but a lot of them you can just tell by looking at them. You really have the midline's -2. It goes this much higher and this much lower. This one, it just goes from +1 to -1. Here's one about gravel in a processing plant. Some pretty cool problems. Anyways, final exams tomorrow. No homework due. Just make sure you prepare yourself for the final exam tomorrow. And you have any questions or anything you want to talk about, stay on the line. Otherwise, I'll see you guys tomorrow. You guys are the sole survivors. Bye-bye.
All right, bye-bye.
All right. Elizabeth, you curious? You want me to send those to you?
Yes.
All right. I'll send them to you, all right? Yeah.
Yeah.
They're tricky, but if you're just curious, you want to see them, and if you want to try them and send them to me, I'll be happy to take a look at your work. This week or next week or the week after. Okay. All right.
Can I just you send them to me?
Yeah, sure, Mata. Yep, I'll send them to you too. Yep.
Thank you.
Yeah, beautiful. And same offer. If you end up trying them, you want to send them to me at any point, send them to me. I'll take a look at them and give you some feedback.
Right.
All right. Bye-bye.
Can you send them to me too?
Sure, on. Yep.
Please.
I will
Thank
do that.
you.
Yep. So Elizabeth, Mata, on. Okay.
All right. See you tomorrow.
Yeah, and obviously the same offer applies to you. If you end up trying them, just send them to me. I'll check it out, see how you did. Okay.
Okay.
All right. Bye-bye.
Bye.
Thanks, Mr. Kaplan. I appreciate that. That was really helpful. If I was smart, I would have thought to bring a side-by-side graph. So thank you very much.
Okay, well, I'm not sure I've always found that in the math classes, this is covered so quickly, and then I used to think the math students just figure this out right away and they don't have to take physics. But that's not the way it works.
Yeah.
The physicists put a lot of emphasis on interpreting graphs, and sometimes if you start with an acceleration graph and work backward, that's not so easy. I mean, it takes a lot of thought.
Yeah. So anyways, tomorrow is just the exam. If you'd like to hop on the line to, just say hi to the students or anything, feel free. But otherwise,
Okay.
we won't need you for any help because
Okay.
they're just going to be working on their exam the whole time.
Is Ariana still here? I don't want to interrupt her. I see her name here. She's still.
Yeah. How you doing, Ariana? Sometimes it takes them a while to turn on the mic, and then sometimes people, I think, they step away. They got to go to the bathroom or something.
Okay. Because yesterday I felt bad. I started talking.
Oh yeah. No.
Do you know? Is there a meeting? A 10:30 meeting tomorrow? Do you know?
Let me see. I assume there is, because
Okay.
he at the last one he said penultimate meeting. Yeah, I lost power yesterday too for about 3 hours or a little more.
Yeah. Well, we lost power and I took out the generator, it's this expensive Honda generator with electric start and all this ritzy stuff, and then it quit. And I was pretty upset until I realized that mice had gotten in there and eaten the control wires, so I couldn't really blame it on Honda. And I couldn't get it. I almost could fix it. I could almost reach in there, but I couldn't. I'm going to have someone take it apart, I think.
Wow.
But fortunately, we didn't get a whole lot of rain because the pumps here stopped when there's no power. I mean, it's just not good. So what time did you lose power?
We lost it about a little before 4:30, and I'd say we got it back. Actually, it was closer to 8, like by 8 o'clock. I'd say we got it back. And well, the wind wasn't even bad when we lost. Bad shortly thereafter.
Well, the police were sitting right at the next house over for several hours. I think there was a wire down there waiting, and they blocked the street. So I think it's right about half a block away from here. I'm going to have to take a walk today and take a look.
Huh.
And then at 3 o'clock this morning, you get the workers out there. the utility workers and, you know, the flashing lights and the beeping trucks and all that kind of